Welcome back. For our last lesson this week, we're going to look at a technique which will let us solve integrals that we weren't able to do before. Now, in the past, when faced with integral with a square root, we were hoping that whatever we plugged into the square root would have a corresponding derivative outside. So if we had some kind of an x out here, we could do a u substitution. But if we don't, then we're kind of stuck. We don't have a good tool. Or do we? Because we remember that we were just using trig identities to make things look different. And if this were not x, but instead sine of x, 1 minus sine squared just becomes cosine squared. And the squared and the square root would cancel out. And we would just have a trig function that we could integrate easily. And same thing here. If this instead of an x were a tan x, then 1 plus tangent squared of x becomes secant squared of x, and the square root would cancel it out. So the idea here is instead of doing a u substitution, we're going to substitute x with a whole trig function. This is called a trig substitution. It's a technique of its own, and it's super neat and powerful because sometimes we don't remember what was supposed to look like a trig function. For example, if you had the integral not of this, but 1 over it, a lot of people don't recognize it as being arcsine. If you use a trig substitution, it'll come back to you, and you'll be able to solve it anyway. So this lets you solve stuff that you didn't necessarily remember how to do. Super nifty. So let me show you the technique. Let's do the first one. Suppose we're doing the integral of square root of 1 minus x squared dx. And it can look a little bit complicated, but as long as basically you have something squared here, whatever's being squared here is what you're going to set up equal to your trig function. So we're going to set x equals, in this case, sine of theta. It's traditional to change the variable to the Greek letter theta when you're plugging it into a trig function. So we're going to go with how the book does it and how 99% of the world does it. We're going to let x be the sine of theta. But we still need to find what dx is because we're going to have to replace it. What is the derivative of sine? It's just cosine of theta. And because we're taking a derivative, we have to multiply by d theta, which means dx d theta should be cosine of theta. And in fact, that's exactly right, because x was the sine of theta. So we have the two pieces. We can now go ahead and change every occurrence of x into a sine of theta, and the occurrence of dx will be changed into cosine theta d theta. And that's it. That's how we do the substitution. So we substitute, we're going to integrate, and then we're going to have to talk about how do we back substitute. So let's go. Let's do this. Our substitution becomes the integral of the square root of 1 minus sine squared of theta. And then dx becomes, outside here, cosine of theta d theta. So the reason why we chose sine is because 1 minus sine squared is cosine squared. So this is good. Notice that we could have gone with x being cosine theta, and it would also have worked. In general, if you can substitute sine, you can substitute cosine, but everybody goes with sine because the derivative is positive. It's just easier. So I would recommend just stick to sine when you're doing a 1 minus x squared substitution. So let's go. We plug it in. 1 minus sine squared becomes the integral of the square root of cosine squared of theta times cosine theta d theta. Okay. Now, when we integrate, when we look at the square root of cosine squared, this is going to simplify down to the integral of cosine theta times cosine theta d theta. And now we have to integrate the product with cosine and cosine. This is cosine squared. We're going to need a trig identity. The trig identity says that the cosine squared of theta, well, I should write it the other way. the cosine of 2 theta. Oh gosh, what's the identity? Let me pause, and then I will get you the identity. All right, so I had to look it up, but the identity is the cosine squared of theta is 1 plus the cosine of 2 theta over 2. I want to make sure I didn't just by purpose put in some mistakes by putting in the wrong formula. So this identity is going to help us change how this looks. To instead of cosine squared, we're integrating this expression, which is 1 plus cosine 2 theta over 2. And again, because it's over 2, I can pull that 1/2 in front, and it just becomes 1/2 of 1 plus the cosine of 2 theta d theta. Great. So integrating the first one isn't bad because the integral of 1 just becomes theta. Integrating cosine of 2 theta is a quick u substitution. So if u is 2 theta, then du is 2 d theta. So d theta just becomes du over 2. And so I end up with 1/2 of the integral of 1 is going to be theta plus the integral of cosine u du over 2. Right? D theta is du over 2. So right here, which is going to be 1/2 of theta. The integral of cosine u is sine u. So I'm just going to get sine of, and u is 2 theta, 2 theta with a 1/2. So I get 1/2 of theta plus 1/2 of sine of 2 theta plus c, our constant. But we don't want an integral with thetas. We want an integral with x's. And we don't have a sine of theta left. We have a sine of 2 theta. So we're going to have to use another trig identity, which says the sine of 2 theta is 1/2 the sine of theta cosine of theta. So one more thing that we're going to have to go through. And once we have this last piece, then we can replace sine of theta by x, but then we're going to have to figure out what to replace cosine of theta. Well, cosine of theta is going to be something that we figure out by drawing a right angle triangle. So if this is theta, this length here is 1, right? And x is the sine of theta. So the sine of theta is going to be x over 1. It's opposite over hypotenuse. So this is x, this is 1. The sine of theta equals x over 1. So sine of theta equals x over 1. So my picture matches this equality, which means that now that my picture matches, I just need to solve this length in terms of 1 and x. But it's a right angle triangle. So this must be the square root of 1 minus x squared. And so now I know exactly what my cosine is. My cosine is going to be the square root of 1 minus x squared over 1. So I'm in business. So I get 1/2. Oh, I have a theta. How do I back substitute? Well, if sine of theta equals x, theta has to be the arcsine of x. So we have arcsine of x plus 1/2 of sine of theta is x, and cosine of theta is the square root of 1 minus x squared plus c. Oh, fun. And that is the end. So this gives us an actual way to find an antiderivative to this expression, which we couldn't do before. Yeah, there's a lot of steps. These are a little bit tricky, but they're not that bad. So I would encourage you to try this one on your own. To do this one, you're going to need, instead of x equals sine of theta, you're going to need to set x equals tangent of theta, because 1 plus tangent squared is going to give you secant squared. So when we integrate, we're going to be looking after the u substitution at, well, we should do the dx, right? Dx is going to, well, let's just do it. Looks like we have to do it. So I'm going to do this one in the next video, just so that we don't run out of time. And I'll see you there.